biologist tests a 1/10 of a milliliter sample of lake water and counts 30 specimens of a specific algae. Using a proportion, the biologist estimates there are 300,000 specimens per liter of water. What is the most critical assumption underlying this estimate? Now let's break down the math first. You start with 30 specimens in a tiny 1/10 of a milliliter drop. Now you want to scale it to an entire liter, which is exactly 1,000 milliliters. Now, to justify jumping from a tiny droplet to a massive volume, your scaling method relies on setting up a linear proportion. Now here's what that proportion looks like on paper. So we set 30 over 1/10, and that is equal to our unknown variable, x over 1,000. When you cross multiply and solve for x, you are multiplying your count by a scaling factor of 10,000. Now that gives us a final estimate of 300,000 specimens per liter. Now, the math is flawless, but statistics and real-world biology does not always play by numerical rules. Now, this calculation only works under one condition. Let's keep that in mind as we look at our options. For option A, for our math to hold true, the algae must be uniformly distributed. So if your tiny 1/10 of a milliliter sample was accidentally taken from a dense, unrepresented cluster of algae, your entire estimate of 300,000 drops to pieces. Now it becomes highly inaccurate because your sample did not represent the whole. But what about options B, D, and C? Now, while things like temperature, stability, and neighboring organisms can in fact affect how algae behave over time, you do not change they do not change the validity of our count. So, sure, you need a good scope to see them, but it does not dictate whether your lake water is mixed evenly. So, the best answer is answer choice A. The small water sample was representative of the entire lake. Scaling up a small sample always assumes that a small piece tells the true story of the whole puzzle.